So welcome everybody for our new series. So Rosa and Mike are going to spend the next 6 lectures to teach us about their paper on symmetric group characters as symmetric functions. You should be able to access the paper in an email that I sent you. And so today Rosa would be our host and Mike would be the next 2 hosts for the same topic. And we are going to record it, and with the consent of both Rosa and Mike, I will be able to post the recorded video on the YouTube. Okay. Anyway, so now let's give the time to Rosa, and yeah, all yours. Thank you so much.
Thank you. So as Anna said, I'm going to be talking about this paper, Symmetric Group Characters as Symmetric Functions. And basically the objective of the lectures are to introduce a non-homogeneous basis of symmetric functions such that they evaluate the characters of the symmetric group, and their structure coefficients corresponds to the Kronecker product under the regular product of polynomials. And we will end the lecture series by giving an application to finding special cases of some Kronecker products. Today, we are going to assume some familiarity with the representation of the symmetric group. I know that Mike will say a little bit more about this during the next lecture. But I don't want to forget to thank Anna and Jim for organizing this seminar series and for inviting us to speak. So I haven't prepared slides ahead of time. I just prepared the first only the first slide. But the lecture title of today is Symmetric Polynomials as Characters of GLN, to remind you and basically tell you the philosophy that we are taking in this lecture series. And today, for instance, my objective is to give you like a little introduction to three things that play a key role in everything that we do: Schur-Weyl duality, Kronecker and reduced Kronecker, and the partition algebra. So the main idea is to motivate and give you some preliminaries of what's known. So I want to begin by saying that today I'm talking about the general linear group, and there are 2 ways that I usually think about it, as n by n matrices, or you could think as GLD, right? And this is the linear transformations where this vector space has dimension n. And when we write it like this, we think of linear transformation. So we can think of it as both ways. So for the combinatorics that I'm interested today, I'm going to be talking about polynomial representations of GLN. And basically, so perhaps the best thing to do is to just give you a couple of examples. So from GLN to some GL different n. And for example, maybe I should say, so here we can think of it as a homomorphism. But when we think of representations, we can also think as having a vector space, some vector space with an action. So we will think about it in both ways of GLN that give rise to the linear transformations. So 2 examples of polynomial representations, like so for example, I'm going to call this one rho all throughout. And for example, like if you take a matrix A, B, C, D, you can get A squared, AB, B squared, 2AC, AD plus BC, 2BD, BD, and D squared. So as you can see, all the entries in the resulting matrix, right, is a 3x3 matrix, and all the entries are polynomials. So this is what we mean by a polynomial representation. All the entries are polynomials. And in this case, if you are familiar with a representation theory, you might realize that this is just Sim2 C2. That's the vector space, the symmetric tensor. And well, maybe I should have started with the defining representation. So defining representation. Which simply, so I'm going to call it phi because I will be referring to it. And this for any n to GLN, and what it computes is just itself. And in this case, the vector space that corresponds to it is just Cn. Like I'm talking about complex representations all throughout, as you can see. So a polynomial representation is called homogeneous. Is homogeneous of degree m if all entries in row A are homogeneous of degree m. So for instance, in this example, this one is homogeneous of degree 2, and this one is going to be homogeneous of degree 1. And so there is a proposition that says that if you give me any representation of GLN, homogeneous polynomial of degree m, then there exists a multiset m that it corresponds to the representation of monomials when we use this usual notation for polynomials, such that the powers all are up to m, and containing exactly n elements, so m monomials.
Rosa, you want subscripts on those last alphas of n?
Yeah, thank you. Alpha sub n, thank you. So it contains exactly n monomials, and there could be repetitions. That's why it's a multiset, such that if A is in GLN with eigenvalues data 1 up to data n, then row A has eigenvalues data n, data alpha, for all alpha, for all x alpha in the multiset. So what this is saying is that if, which shouldn't be, guess, hard to believe, that if all the that the eigenvalues are going to be monomials in the, like all the eigenvalues of this matrix are going to be monomials, all of the same degree. So that's what this theorem says, what this proposition says. So so here, in order for running example, like the two representations that I had, when you have the representation Sim2 C2, Then in this case, we call it rho, and then in the eigenvalues of the matrix look like this: x1 squared, x2 squared. So, and for the other example, for the defining representation, so if you do Cn, then the multiset is just x1 up to xn. So this is, so why are we doing this? Is because we want to define the characters of GLN. Remember, the title is characters as like the characters as symmetric functions. So so the character of a if you give me any representation of GLN, we can define a function phi corresponding to this representation that goes from GLN to C. And what this computes, so if you want to compute the character of the representation, you simply so add an element in the group A. What you compute is the trace of rho of A. Which we simply write TR in, but what this is in from linear algebra is the sum of the diagonal entries in row A, or equivalent, or one can show that is the sum of the eigenvalues of row of A. So for our example, the two examples that we have chosen, for the first one, the chi rho, which is the symmetric tensor, you get data 1 squared plus data 1 times data 2 plus data 2 squared, where data 1 and data 2 are the eigenvalues of A. And for the defining representation, which we call phi, this is just data 1 plus data 2 plus data n. Okay. So in general, the characters of the general linear group are going to be, so if you have a representation, it's going to be a polynomial where you are summing the eigenvalues, but as we saw from the propositions, these are going to be just monomials in this multiset that the proposition told us existed. So this is in general a homogeneous polynomial. And so the thing that I want to make a note of, so let me call this a star, like, because this is kind of key in what we are going to do over the next 6 lectures, is that to find the characters, the character value of an element A in GLN, what you have to do is you evaluate the polynomial at the eigenvalues of A. So there is this big theorem that I'm going to record here. The theorem about representations of the general linear group. So every polynomial representation of GLN is the direct sum of irreducibles. So that you can always decompose them into irreducibles. We are going to be using these facts a lot, so I just want to keep track of them. two polynomial representations of GLN are isomorphic if and only if their characters are the same. Three, the irreducibles representations, polynomial representations, all the representations are polynomial of GLN are indexed by partitions of any number, but of length less than or equal to n. So they have at most n parts. But the most important one, which is the key here, is that the character of an irreducible a polynomial representation of GLN is, so remember they are indexed by partitions now, is going to be just a short polynomial in the variables x1 up to xn, where it's the same as this n. And then, so here, so this basically, I'm going to be using a lot. So perhaps I should say, how is this proved? How is this theorem proved in the literature? Like, we will not be able to show all the details because it requires kind of like a course in representation theory. It builds up to this, but the idea of the proof is to use what people know, what is known as Scherr-Weil duality. Basically, you use the fact that you know the representation theory of the symmetric group, and you use it to figure out the stuff about the representations about the general linear group. So here is the idea of how it works. Because I will be talking about restricting this idea in order to define later when we are doing the characters of the symmetric group. So, so the idea goes as follows. So you let V be equals to Cn, and GLN acts on this. So you have two actions. You have so you can, if you have Cn, you can define V tensor K to be the K-fold tensor product. And at this point, since remember that this is the defining representation, if you act by multiplying this by A, this gives you the defining representation. So this one is going to be a representation of GLN. And basically, like when you decompose it, it will contain all the representations of degree homogeneous of degree K for GLN, for any n. So, so this is an important representation for GLN. So there is an action. So there is an action of GLN. So you have two actions. GLN acts diagonally on V tensor K. So what does this mean? It means that if you take an element A in GLN and you have V1 tensor VK, this is gonna just be, you just do matrix multiplication if you like to think concretely on each of the components. So it acts diagonally for any A in GLN. And you also have an action of SK. SK acts on V tensor K by permuting factors. And sometimes people call this the right action. So I'm gonna write it like this: V1 tensor vk, and in the literature is usually written as sigma 1 inverse to indicate that it's permuting the tensors. So it just does a permutation. I say this because later I'm going to have another action of another symmetric group, and that is going to be the left action. So here it's in SK. So the key observation in here is that these two actions commute. So it doesn't matter if I apply the action of SK first and then I act with GLN, or if I act with GLN first and then with SK, the output is going to be the same. And why is this important for us? Is because this implies that if I form the group SK, so this is the direct product of two groups, right? This group acts, the action is well-defined, acts on V tensor K also, and the action is well-defined. But not only, I guess the important thing here is not only that the actions commute, and then this leads to the action of these two groups, but there is another very critical idea here, is that the action, I guess in short, one can say that the actions centralize each other. So what does that mean? So that means that if you want to know, right? So when you have an action, that leads you to coming up with like a set of matrices, one for each, or a set of linear transformations, one for each element that acts, and it gives you a linear transformation. So if you put all the collection of all those linear transformations that you have, and you ask, what are the linear transformations that commute with all of those, right? Then the answer are going to be the linear transformations that you get from the action of SK. So how do we write that? So for instance, I'll write one of them. So if you look at the shortcut way that one, like, let's say I want to look at GLN V tensor K. So what is this? So this is the set of linear transformations AF from V tensor K, maybe I should do V tensor K that commute with the action, or I should say diagonal action, of GLN on V tensor K, then that is actually the CSK, the group algebra of the symmetric group. And similarly, if you want to look at what commutes with the action of SK on V tensor K, right, this is going to be I guess the group algebra of the general linear group, or often what people say is generated by the diagonal action of GLN on V tensor K. So this idea that that's all that commutes, nothing else commutes, is kind of like the critical idea that one uses in the proof. But perhaps so now we have that V tensor K is an SK cross GLN representation. So we can decompose it as a representation of these two groups. And when you decompose, so the representations of a direct product of two groups is simply the representations of this. You just put them both together with a tensor symbol that is just putting them together. So you get the direct sum. Here you have lambda is a partition of K. And then the length of lambda has to be less than or equal to n. And here what you will get are, here you get the representations of SK, and you put a tensor to indicate you're putting them together, and you have the representations of GLN. And you have the same symbol, like for both of them, which gives what is the duality. For every representation, polynomial representation of GLN, you get a representation of S lambda, and for every representation of S lambda, you get a representation of GLN. They come together like that. So these are the irreducible representations of SK, and these are the irreducible polynomial representations of degree K of GLN. So so let's say we want to compute the
Pardon me, Rosa, a very minor thing in that top thing where you're saying the centralizer should be CSK, if you scroll up a little bit, you mean the image of CSK inside that endomorphism.
Yeah.
So it's,
yes.
Yes.
Yes. So yes, so we are talking about actions, right? So
right.
so maybe here where we are talking about the linear transformations. Yeah, because it's later you're going to see a different one. Linear transformations arising from action. Thank you.
And then if n is less than k, you have to mod up by the ideal generated by like the anti-symmetrizer over Sn inside Sk or something to get the...
Right. So perhaps here I should say in most of the work that I will have, that n has I will want for this to be maybe I should say isomorphic to k.
Okay, thank you.
Okay, thank you. Otherwise, there is kind of like, you don't get everything, right? Okay, so okay. So now I wanted to compute the character, since we are interested in characters. Compute the character of the tensor K. So, and one can do it in two ways. You can do it directly. So you take an element sigma in A contained in SK cross GLN, and you want to compute the trace of this representation of this action. So this is going to be the trace of the linear transformation resulting from the action of sigma cross A on the tensor K. So if we compute it by looking at this, right, then this tells me that this is just going to be the sum of lambda partition of K, length of lambda less than or equal to n, the characters of the symmetric group, so the character of the symmetric group SK evaluated at sigma, times the trace of the polynomial representation indexed by 8, like that, okay? So So this is if one computes it with just from this comes directly from this formula. So so I did, so it would take too long to give you an argument. So maybe I say it can be shown, but if you're interested, we can talk after how. So suppose that sigma has psychotype mu. It can be shown that the trace of sigma A is equal to the power symmetric function. This power symmetric function, where these right here are the eigenvalues of A. And perhaps since I'm kind of skipping like the argument here because I want to get, if we have time, I can kind of at the end show you, but like, so maybe I do an example. So suppose that I have n equal to k equal to 2, for example, and I take the element 1, 2, and the diagonal matrix x1, x2. So this is in S2 cross GL2. And I want to compute what this trace is. Well, in this case, V is equals to C2 and V tensor 2, right? If I choose the standard basis for C2, I can say E1 tensor E1, E1 tensor E2, E2 tensor E1, E2 tensor E2. And if I compute the action, one is acting diagonally and the other one is acting by the factors, the matrix that I will get corresponding to this element will look like this. It's a 4x4 matrix. And you can kind of check yourself that that's what I get. So if I compute the trace of this matrix, right? The trace is equals to x1 squared plus x2 squared, which is P2 of x1, x2. And here, right, the psychotype, sorry, the psychotype of this is 1, 2, and the eigenvalues are x1 and x2, as kind of can be seen. So anyways, so if we go back to our formula right here, right? So now we have, right? So from here we have that P mu of data 1 up to data n, right, is equal to lambda, chi lambda, sigma, and sorry, what is it? And the trace here of rho lambda of A. So, but by Murnaghan-Nakayama rule, right, we know that P mu can be computed like that. If you actually carry it out, this is going to be sigma of S lambda, sorry, chi lambda evaluated S lambda of data 1 up to data n. So with these ones are the sure polynomials, and remember that's what we wanted to show. And this follows because the chi lambda, if you look at this set, this is linearly independent. From the theory, from the representation theory of the symmetric group. So you get that it has to be those exact elements. So this shows that the characters, right, that these irreducible polynomial characters are exactly the sure polynomials, and that to compute the character of this, you have to evaluate the sure polynomials at the eigenvalues of the matrix. So maybe I record it as a main fact one, because these are kind of like the things, the irreducible characters of GLN are sure polynomials. Evaluated at characters, at eigenvalues of A in GLN. So this is the first thing that we want. So now let's talk. Let's talk about tensor products, because basically we are interested in the Kronecker tensor products. So if you have to represent, so I'm going to use B lambda and B mu for irreducible polynomial representations of the general linear group, are irreducible polynomial representations of GLN. One can define another representation, B lambda tensor mu with action, with diagonal action. And simply means if you have an element in GLN, it acts diagonally, as we saw on each of them. And this is a representation. And like the important thing for us is that that if you want to, so the character of this representation is the product of the two polynomials, like S lambda and S mu. So if I wanted to decompose the tensor product, it is equivalent to decomposing the character, and this is equal to nu. And the multiplicities are the Littlewood-Richardson coefficients. And I'm not going to go into it, but there are many different rules, combinatorial interpretations for computing these coefficients. So, so the main fact two that I want to record is that decomposing tensors of irreducible representations of GLN, well, polynomial, corresponds to products of sure functions. And there is a rule to compute, and it is the Littlewood-Richardson rule. So then now I want to talk about Kronecker coefficients. And the Kronecker coefficients occurred in this, but now, so here I'm going to use a different color because I want you to notice that I'm using N here. So I'm going to start thinking not of SK, but of SN now. So if you take two representations of the symmetric group, you can also form the tensor product. And in the similar question, you want to be able to decompose it into irreducibles. And these, you have these coefficients in lambda, mu, nu, and we, depending if we want to distinguish, sometimes you will see it as lambda, mu, nu, in similarity to Littlewood-Richardson coefficients. And these are what are known as the Kronecker coefficients. And here, all lambda, mu, and nu are partitions of N, like they are all. Here for the general linear group, you have like, you know, any, because this kind of gives you the degree, right? So this is just the sum of the size of lambda plus the size of mu. But here you have all are representations of N. So for example, let's say you could do S2, 2, Kronecker S2, 2. And if you were to compute it, you would get S4, S1, 1, 1, 1, and S2, 2. And just I kind of have the characters table here, like I didn't like perhaps copy or maybe copy so that you can see. So here you can, if you check, right, you will notice that if you do the character, right, for 2, 2, if I look at it as a vector, right, is this vector, right? So if I do the Kronecker product, which is just pointwise product of the two functions, you would get 4, 0, 1, 4, and 0, right? And then what this is saying is that this should be equal to 1, 1, 1, 1, 1, plus the character of the sign representation, plus the character of this representation. And if you do the sum, it works out. So there is this stability phenomenon that happens, which is the Murnaghan stability. And what it says is the following, that if you take the Kronecker product indexed by 3 partitions, like lambda 1, lambda 2, etc., and mu 1, mu 2, etc., and nu 1, nu 2, etc., that this number is going to be less than or equal to the number that you get when you are actually adding 1 to each of them. So maybe I write lambda 1 plus 1. And then all the other parts stay the same. Lambda 2, you do a lambda mu 1 plus 1, mu 2, and nu 1 plus 1, nu 2, etc. So that this increases, and that the stability, it says that eventually it becomes constant. And I didn't, so that I didn't have to write it, I kind of copied one example that copy an example so that you could see. So the example here, right? So this is the one that we showed above with a character table, right? But if you increase, right here, we're simply increasing the first entry, right? Like the first entry in the partitions. And the new stuff that shows up is in red. right? Like you get whatever was there before, all you do is you increase the first part of the partition, right? And then some new stuff appears. And then you do again increase, right? And you get some new stuff and maybe some new coefficients. The coefficients could increase, right? But eventually it will become stable. And this stabilizes, and then no matter what n you take after, 7, right, 8 here, like it will give you the same all the time. So these coefficients, the coefficients that occur, the stable coefficients are known as the reduced Kronecker coefficients. And here they can be for any 3 partitions, like they don't have to be partitions of n. And these are the stable limits of the sequences. And they are known as the reduced or sometimes stable Kronecker coefficients. So maybe, so there is a theorem of that we prove with Mercedes, who happens to be in the audience, and Emmanuel Briand, that there is a very beautiful relation between the Kronecker coefficients and the reduced Kronecker coefficients. And they are simply given by this formula right here. And so this right here means you remove, so if you take a partition, it simply means remove this first row. And this other notation, so if you have any sequence U1, U2, etc., you can construct a sequence I by adding 1 to all the first I minus 1 entries in the sequence. Then you remove the I, so you remove, and then leave everything else the same. So it says that you can obtain like any Kronecker coefficients as a sign, as a sign combination of the reduced Kronecker coefficients. So so once you figure out up to sign, you can figure out all the other ones. So well, so a main problem, right, is to find a combinatorio for a formulation for the Kronecker coefficients, or interpretation for either the Kronecker coefficients or the reduced Kronecker coefficients, alpha, beta, and gamma. And so the idea that we have been pursuing with Mike is that we want to think of the symmetric group as being contained in GLN, which means that we want to think of this as n by n permutation matrices. And the reason is, like, similar work has been done for the orthogonal group, for example. So there is kind of evidence that if for some subgroups, you can actually carry out all the work that we are trying to figure out for this problem. And so the idea is to think like this, and to, I put in quotations, we want to replicate, because it's not exactly replicate what worked for GLN. So we will call this the restriction approach. So the first order of business was to restrict the Schur-Weil duality. And so now I'm going to think, since I'm thinking of the symmetric group Sn as being contained in GLN, I'm going to think that Sn acts diagonally on V tensor K. So this is a different action, right? Because when you act, and to denote that it is a different action, you get V sigma 1 tensor V sigma n. You're actually multiplying by the permutation matrix. So for example, like, you know, if you had the permutation 1, 2 acting on the standard vectors E1 tensor E1, it would map it to E2 tensor E2, while the permutation of factors would leave it invariant, right? So it's a different action. It's the diagonal action. And then you ask what commutes with this action, because you want to figure out what the centralizer is. And so, and the idea is that maybe since kind of have 10 minutes, I can, so I'll tell you the answer, and then I will kind of backtrack as much as needed to maybe explain how things worked. But the idea is that if you look at Sn, and here I should say I'm talking about actions, right? So when I write this, is this diagonal action on V tensor K, right? So I have this diagonal action and I want to know what commutes with it. So when n is greater than 2k, like that, this happens to be one algebra that is pkn, and this is known as the partition algebra. As the partition algebra. And so how's the partition algebra defined? Because we are going to be having characters of these floating around in the formulas that we will kind of come up with. So the partition algebra, maybe, I'll say it. So, so notice that if a linear transformation or a matrix, right? If a n by k by n by k matrix A commutes with the action of Sn, right, is going to be a matrix that is going to look like this. It has many indices for the tensors. And one can actually show a lemma. Is not very difficult to show that A is going to be in this centralizer if and only if, so I'll write them as vectors now, to not write all those indices. If this happens, where a sigma of I is simply I sigma of 1, I sigma of 2, etc. So it's just kind of like acting on this. So maybe give a little example. So because this looks kind of maybe a lot of notation. So if n equals k equals to 2, A would be equal to A11, 1, 1, A11, 1, 2, A11, 2, 1, A11, 2, 2, for example. And then here you would have like A11, 1, 1, etc., right? And what this lemma is saying is that if it commutes, this would have to be the case. for example, like, so these are kind of some examples, like 1, 1, 1, 2 equals a 2, 2, 2, 1, like, etc. Like, so you will have every time that you apply the, maybe I delete it. And what this, so perhaps like one thing to notice is that if I let these symbols be like the indexing set for these ones, just to differentiate them, this be 1 through k, like the indices. And so to differentiate what goes on the top and what goes on the bottom, k bar, like just put bars to indicate that is the thing that is on the bottom, then I could
Rosa,
think of,
in the statement of your lemma, do you maybe want sigma of I1 and sigma of I2 instead of the sigma of the subscript? This lemma that you're just talking about now. Sigma of I1, sigma of I2 instead of in the subscript?
yeah. Thank you. Sorry. Yes. Sigma of, yes, because it kind of, I think so. I would have to.
I think Alex meant sigma of I1, not as a subscript, just sigma of I1 all by itself.
Yes, thank you. Yes. Yes, thank you.
And while we're stopped, I also had a question further up when you were defining the action of sigma, this new action. The
diagonal action.
The diagonal action. Yeah, so I mean, in general, even if you've got a permutation of matrix, sigma of V1 isn't going to be V sub sigma 1, right? It's just going to permute the entries of V1.
Right. But on the standard, right? So if you choose the standard basis,
it has this.
So you're saying the V's are really standard basis vectors. Here.
Yeah. So in this on the
so
standard, right?
It's
like
not for an arbitrary. Yeah. Okay. So the V's have got the standard. Okay.
It's basically That's
okay. That's what I.
So it's just a permutation representation acting on each.
Okay.
And copy of.
Gotcha.
Right. Okay. Good. Okay. So then maybe so I can now say that this looks like like I can kind of write something like this, right? This is a set partition where all of them are equal. This is the set partition where 1 bar and 1 are equal, and 2 and 2 bar are equal, right? This is the set partition where 1 and 2 bar and 1 bar are equal, and then 2 is different, right? So for each set partition, I'm going to get a linear independent a linear transformation, right? So so the idea here is that the set partitions of K union K bar index the linear independent linear transformations that commute with the diagonal action of Sn. So PK n, you could think of it as the Cn span of the set partitions of K union K bar. And let's remove these two. So when you have a set partition, so notice here how there are 2 rows. So what we usually, the way that we usually represent these elements is using diagrams. So here you put 2, 3, 4, 5, and here 1 bar, 2 bar, 3 bar, 4 bar, 5 bar, for example. And you would have like something like this, right? And this would represent the set part. This corresponds to the set partition 1, 1 bar, 2, 4, 4 bar, 2 bar, 3 bar, and 5 bar, for example. And it doesn't matter what this as an element in the algebra. It doesn't matter how you connect them or what graphs you use to connect them. You can use any graphs. So like, for instance, here I'm using a triangle. All that matters is the connectivity. So when people talk in this area about the diagram, they simply mean any graph that that has that set partition corresponding to it. And so, for example, and these are actually encoding linear transformations. So I'll show you quickly how I think of this as a linear transformation. So I can think of this as being a linear transformation from tensors A, tensor B, tensor BC, tensor BD, right? And this will be, so what the linear transformation does, it checks that A is equal to B is equal to C. So this is the Kronecker delta that checks if things are equal. So if they are equal, it says, okay, and then it says this is gonna be VA, tensor VA, tensor the sum of VI, tensor VI, I equal 1 up to N. So that's what this linear transformation does. So for example, f of, if I choose the standard basis vectors, for example, V2, V1, V2, this is 0, right? Because the first 3 entries are not equal. But if they are equal, so for instance, if you have this is going to give you a sum of two things, V1, tensor V1, tensor, for n equal to 2. For example, it's going to be higher if V1, 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 tensor V1, plus V1, tensor V1, tensor V2, tensor V2. Like, so it would give you the sum of this. So it kind of gives you an action on tensor space. And it's these linear transformations that are arising from this action that commute. And the product is kind of like done very nicely, similarly as when you multiply diagrams for the partition algebra, sorry, for the symmetric group. You get this like that. And so let's say this is my diagram D1, and I'm computing D1 times D2. And then you put one diagram on top of the other. Like that. And what you do, in the usual thing that you do is you identify this in here and just follow connectivities. And then you look at factors that are completely contained in the middle. Like, so like this kind of like graphs. So then in this case, there are two. So you have n squared, and then you look at the way that the remaining things are connected. And in this case, we get this. Oh, I connected it in the wrong. This one is disconnected, and then I get like that. Okay. So then it gives you a well-defined product, and it is known as the partition algebra. It's called as it is associative. It has the dimension is the Bell number, B2K. It has identity, which is just the one that connects everything like that. And when it satisfies all the conditions. So right now I make the connection. So if it is known so that there is a Sure-Bio duality for Sn in the partition algebra pKn. They are in Sure-Bio duality. So both act on V tensor K. The actions commute. Which gives you a well-defined action of this algebra acts on V tensor K, which implies that if you decompose V tensor K, you should get a lambda is a partition of n, and if you add lambda 2 all the way to lambda L, this is less than or equal to K. That's how the numbers come in here. And these are the representations of the, these are representations irreducible representations of pKn, and these ones are representations of the symmetric group. So in here, I'm assuming that n is greater than or equal to 2k, because in this case, it's going to be this partition algebra happens to be semi-simple, so it will decompose. So if you compute the character of this to tie back to character of this at an element D sigma, some diagram, right? pKn cross Sn, you will get, this is the character of V tensor K on this side, and on this side you get the characters of the partition algebra, which will occur in the formulas that we will have next week, Sn lambda sigma. Well, these are the characters, but we are thinking of Sn as being contained in GLN, right? Which actually says that the character of V tensor K, remember, was equals to P, some P mu, right? X1, some power symmetric function Xn, but now you are only evaluating at eigenvalues. So we should be able to get this, right? Using the power symmetric functions, evaluating at eigenvalues of symmetric matrices, of permutation matrices or permutation matrices. So the conjecture that we made a long time ago is that you would actually get something that looks like this. Where this means you remove the first row. And these x1 up to xn are eigenvalues of the sigma in Sn, right? Thought as a permutation matrix. And this, so basically the idea was that, you know, whether we could find some symmetric functions, right? That when evaluated gave you, so maybe to contrast in the classical duality, right? You would have that P mu equals some, but now characters of Sk here at some, evaluated at some sigma. And here you had the sure functions, right? So now the question was whether these things existed, and furthermore, right? So the second thing, if you multiply two such things, just this is a product of polynomials, regular product. when you expanded it, they actually gave you the reduced Kronecker coefficients as structure coefficients. So this is, kind of what it was. And I didn't know at all how to define this a symmetric function, let alone one that satisfied all these conditions. But the theory was saying that it should exist, something like that, like it has been done for the orthogonal groups. So at this point, I contact Mike and I ask him, how do you go about defining asymmetric functions, more if it is asymmetric functions that evaluate at irreducible characters? So this right here should be evaluating at irreducibles. Evaluates at irreducibles of the symmetric group Sn, right? So I wanted something that did this and satisfy this, right? And so that started, I think, a very fun collaboration, and Mike will pick up, and I think he will talk about evaluations of symmetric functions and how the existence and how they were defined, how these functions were defined. So I'm going to stop, sorry.
Thank you so much. Any questions? Yeah, Brendan.
Yeah, thank you. Great talk. So one question, you had this result where you were saying that a Kronecker coefficient is an alternating sum of reduced Kronecker coefficients. You had proven it with some collaborators.
Yes, this one.
Yeah. So I mean, the proof, I imagine, is quite involved, but like, is there some idea as to like what goes into proving that?
Okay, so let me think, because I haven't thought about it in a while. Mercedes is also here. Mercedes, do you remember? Because it was with Mercedes, so I can actually look at the paper.
I think it was because you express the true function as using the Jacobi through the identity and develop the determinant, and then you get the alternating sum. I think that was the basic idea.
Okay, so it's a determinantal identity that's
Yes.
kind of like hiding behind this, or
Yes,
okay.
yes.
Okay, very nice.
I also have a question. So it was earlier talking about the stability. So like, do we know when is the, like, what is the criteria for the smallest, like when did it start to stabilize? Like in this example, it stabilized at
so
like
it's
6.
so we actually have so there are a global bounds, and there are also local bounds, right? So the local bound would be when there's a particular one, right? So for instance, this one for 2, right, stabilizes at this point, right? And then after that, it is stable. But if you want to know the global, there is a very beautiful formula that we proved in the paper, again, with Brian, Orellana, and Rosa, like this paper. We actually, so if you have if you have the Kronecker product is, sorry, if you have the Kronecker product of 2, maybe I say k lambda chi mu, right? So it is equal to lambda bar plus mu bar plus lambda 2 plus mu 2. That's the bound. And so for instance, if you, in this case, right, everything is 2. So lambda bar 2 is 2, right? Mu bar 2 is 2. So this is 2 plus 2. So this 2, 4, 6, 8. So it says that it should stabilize when at 8, which is exactly when it happens, you see, when 6 plus 2 is 8. This
I
is
see. So
then
so
after that.
basically it's just so that when your lambda and the mu, the first two rows are the same, so that you don't have anything redundant on the first row,
Mhm.
right? I see.
Right. Yeah, so this is the bound, it's a global bound. It tells you when, you know, it stops changing, right? And we also have like formulas for when a particular sequence converges.
Interesting. Thank you. Any other questions? All right, if not, then thanks to speaker again. Great job. Thank you. So the next stop will be next week on Thursday, because July 4th we will have a break, and then Mike would continue on this material on lecture 2. All right, see you all next week. Thank you.